Hello, everyone, and welcome to the 40th Surface Ventures keynote webinar. Please say hi in the chat and tell us where you're joining from today. It looks like we've already had a few people say hello, so glad to see that we're coming through to you clearly, which is fantastic. So please excuse me, triggered the wrong thing. So my name is Dr. Sam McMaster. I'm the content manager at Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and materials science education for both academia and industry. Today, it's my pleasure to introduce Dr. Hannah Zhang from the National Physical Laboratory here in the UK. Hannah is a senior scientist at the Advanced Engineering Materials Group at the National Physical Laboratory, or as many know it, NPL, where she looks after the micromechanical area with a focus on instrumented indentation testing and multi-scale mechanical testing of ceramic materials. She's the UK technical expert on the International Standards Committee, ISO TC164 SC3, concerned with the standardization of instrumented indentation. She also acts as an industry supervisor for several PhD projects. Many thanks to today's partner, Micromaterials. We'll have a short presentation from Professor Ben Beek later in the event, and we'll also be releasing poll questions and handouts from Micromaterials throughout, so we'll highlight when I'm doing those in the chat for you. As we go along, please type your questions into the chat, and I will mark those for the Q&A session later in the event. Just a note, we will have both presentations and then the Q&A. We're planning to go for around 60 minutes today, and we will be sharing a link for your attendance certificates later in the event, specifically at the start of the Q&A session. So without further ado, let's welcome our speaker to the stage. I will bring Hannah's slides up now. There we go. Hi, Hannah.
Yes,
Okay, fantastic.
Yes,
Coming through loud and clear. I'll leave stage now and let you begin.
All right, thank you. Good afternoon, everyone, and I'm Hannah Zhang. Thank you, Sam, for introducing me and inviting me to the Surface Venture seminar, and thank Micromaterials for recommending me for this seminar. And today I will talk about the instrumented indentation testing research activities in NPL, mainly about what we have done and with a focus on micromaterials test systems on multi-technique and multi-scale nanomechanics. And the outline of my talk is, first is the the IIT research activities at NPL, and the second part is multi-technique and multi-scale testing details of the advances and the challenges. And the last part is a case study focused on tungsten carbide grains and the DLC and titanium nitride coatings. So the IIT systems and research activities at NPL starts long before I joined in 2015. And thanks to my colleagues, previous colleagues before me, and continuous development, now we have 4 standalone systems which are located in a closed loop controlled room with high temperature, and moisture control. So we have the Nano 2 system back from 1990s from the CSM, and we have the another room temperature test system, the ultra nano indentation tester, the UNHT from Anton Pang. And this is a dual indenter system. One reference indenter monitors the sample surface position, while the mirroring indenter does the test. The idea is to eliminate thermal drift and compliance for this type of system. And we have 2 nano test systems. which are vintage and extreme, with multi-load height in atmospheric condition and in vacuum condition, respectively. And in addition to the standalone systems, we also have the test system called SIM, which was built in NPL, and it enables us to do the fast indentation for mapping of the large area. And there is also in situ nano indenter from in situ ICM nano indenter from ASMAC. And as for today's focus, the nano test and nano test system for the extreme, the nano extreme with multi-height, we will focus on this system. And with the above setup, the instrument indentation test research activities in NPL includes following two parts. So first is we do a lot of calibration and traceability measurement, and we do regular area function and system compliance checks with certified reference materials, which are also available as commercial products, as you see in the picture in the middle. And the traceable calibration of displacement and load with interferometer and the load cells, respectively, and the direct area function calibration with the FM and 3D legs 3D scanning of the indenter for some high sensitivity measurements. And for the calibration, for instance, on the top right load displacement curve, it shows the importance of the calibration of the thermal drift and the compliance. And there is a NPL good practice guide written by Dr. Nigel J. Knight, which is available for public access. So the second part is to develop new techniques, such as explore the new application of the instrument indentation test regarding to the industrial needs. We carry out research work with direct link with industry and universities, and with the access to the ICM suite and the microstructure characterization, we test a set of materials and format of specimen for the instrument indentation test. Here, so this slide gives us we test the small volumes, for instance, the interfaces, joints, and individual phases in complex structure and microstructures such as precipitates. And with the gallium ion focus beam, we can test the different formats of specimen, for instance, the pillar and the cantilever. So next is we are going to talk about more details on the micromaterial system with multi-technique and multi-scale testing. And mainly for this part, we have three techniques. The first is here is the general details about the nanotest, the extreme system. On the image, on the right side photo is the system equipped with a rough pump and turbo pump, which can pump down about 0.6 cubic meter volume to a high level vacuum within 1 hour. And also for the detailed setup, for instance, the high spatial resolution of about 1 nanometer with nano positional control, and a wider range of temperature from cryogenic to high temperature of about 1000 degrees C that we are testing at the moment. And it gives us option for the atmospheric pressure to high pressure, and also inert atmosphere with backfill of argon or nitrogen. We have tried routine test for hardness and modulus, and also exploring the new test capabilities, for instance, the yield strength and fracture behavior of materials and creep properties. So the first test technique I'm going to introduce is the nano impact. So the setup of the nano impact on the figure on the left is a schematic setup of the pendulum with impact solenoid, which attracts the lower part of the pendulum towards the magnet before the test, and release to start the test. And the load cell on the top as an acceleration force to enable the indenter landing on the surface of the sample at high speed. And the high frequency data sampling enable us to record the depth profile as a function of time. And together, on the right side of the image, together with previous study, the range of speed achieved with this type of setup is by combining the acceleration load and acceleration distance. So we can achieve up to 0.5 millimeter per second of speed. So next slide is an example of the micro impact test on different type of glasses. So there are two types of glasses, fused silica and BK7, with different hardness and modulus values. And you can see the fracture pattern in fused silica is a cone shape, while in the BK7 it's like lateral micro cracks underneath the indent and radial cracks on the surface. So these images were taken by laser confocal microscopes, and which gave us a depth profile of the transparent glasses. So more details about the application of the nano impact will be discussed later in the case studies. And also my colleague Peter Williams also made a video about this. If we have time, we could play at the end about the micro impact test on fused silica. So next technique is the nano scratch. With the pendulum design, the scratch test module enables single and multiple pass wire experiments to be performed, and with potential for the high temperature test without sample, without indenter heating. The image on the left shows a single and multiple ramp test, multiple ramp load test, and the wire and the damage of the coating on a tool steel substrate can be seen from the images on the right after multi scratch pass of 100. There are more details about the nano and micro scratch test as the CERN standard, which was developed recently, led by my colleague Yan Piao, Mark J, led the standard development. And in addition to the images observed after the test, the record of the scratch pass, topography, and the friction force gives a matrix of parameters to characterize the coating wear resistance. Here is an example of the multiple, example of both single and multiple pass scratch test on a composite coating on tool steel substrate. And for instance, on the top left images, from this you can get the yield load and also the load when the radial and the lateral cracks develop as a function of ramping load. And we have done this test on a selection of coatings, and by changing the ramping load and also by combining the multi-load and also the scratch passes, we can develop a map about the material's resistance, the wear resistance of the coating. So we think it's a useful tool in measuring the coating durability, and gives us properties of the including the intrinsic and the fracture behavior. So the next is by combining the intrinsic modulus properties and the yield or hardness values, we could get the stress distribution and the indenter. And here is an example of the stress distribution under the indenter during the scratch test with the seal software. And these two coatings, on the left is the two coatings have similar modulus, but the left coating has a slightly lower hardness compared with the coating on the right. So by taking here the arrow shows where the load was used for to calculate the stress distribution. And we can see the dark region in the coating and the substrate on the left side shows the plastic deformation, and on the right side the plastic deformation only occurred in the coating. So the simulation is consistent with experimental observation, and it indicates that to improve the coating adhesion, the yield, so the coating adhesion can be improved if the interface is only overloaded from the coating side. So the third technique is the environmental control. So here is mainly about the temperature. On the left side is high temperature heating up to high temperature, and the right side is the schematic shows the cooling system for use the extreme system. And for both systems, there are challenges. First is the temperature mismatch or thermal gradient from where the sample surface is and the thermocouple location. And the same as for the indenter side, we couldn't put the thermocouple close to the indenter tip close enough. And the second challenge is to establish the isothermal contact, and which would lead to the thermal drift, and the last one is the system compliance of both system. As a high temperature test has a few decades of research, and to improve the thermal drift and also to calibrate the compliance of the system, the cryogenic test has recently attracted attention due to the drive of the hydrogen economy. So instead of high temperature results, here is some preliminary results from cryogenic test. So the test results are on polycrystalline copper and also on polymer Teflon, which the latter, as you can see, the latter gives a much more severe change of the property with the temperature, while as you can see in the copper, the thermal it has relatively higher thermal drift, and the mechanical properties increase with reduced temperature. We found that by performing the measurement on reference materials and the cross-validation is helpful to interpret the results, in particular at extreme conditions, which can be affected by both thermal drift and compliance with the frame compliance from temperature changes. And we also carried out some scratch tests, shows that with reducing the temperature for the two type of coatings, the friction coefficient reduce, and by post-mortem examination of the scratch pads, we just see the improved wear resistance at lower temperature. And you can see on the right side for the DLC coating after 800 micron, the friction coefficient drop. This is due to the slope on the sample surface. So the part 3 is the case studies focus on tungsten carbide single crystal nanomechanics, mainly with nano impact and up from room to high temperature, and the DLC and titanium coatings with nano impact test. So first is the tungsten carbide, which is mainly here we will introduce the application as we introduce the test on the single crystals. Silicon carbide as a material is one of my group's favorite materials, which we have for more than 50 years of work on the tungsten carbide and cobalt composites. And recently, tungsten carbide or tungsten compounds widely investigated due to its promising candidate material for fusion application as shielding materials. And it has hexagonal crystal structure, and the most common slit systems have been identified and well studied with electron microscopes. For more details, NPL has published a review article on recent metrological approaches relevant to characterization of hard metals and pure tungsten carbide. So this is here is the example of the multi-load indentation on basal plane single crystal tungsten carbide with spherical indenter. Although the test was on the same grain, the plots are quite different. With plot A shows no pop-in, and pop-in occurs observed during unloading in Figure B, and in Figure C is the pop-in during a holding period. And we did a lot of analysis for single crystal tungsten carbide regarding to the surface defects. As plastic deformation is believed to occur by the glide of the pre-existing dislocations, whenever the stress field is large enough to trigger the dislocation motion in this occasion, the popping could occur even during the unloading process. By reducing the indenter size, we were able to get a consistent load at which the popping occurs, which was further calculated to be quite close to the theoretical shear stress necessary for the homogeneous nucleation of the first dislocation loop, and as shown in the following details. So this is the AFM topography of the tungsten carbide at room temperature, and corresponding to the load displacement curve in the slide above. And figure here you see the figure A and B shows a clear six-fold symmetry in the formation of the slip traces on the base plane, and it forms a star shape. And the AFM line profiles in figure C of the indent don't show any large sink-in or pile-ups at the indentation load used, and this observation is consistent with previous research showing that dislocation glide downwards along the 1010 prismatic slip planes and accommodate the volume change created by the indent. And the figures D and E are a twofold symmetry in the slip traces produced on the prismatic plane, along with the formation of the pile-ups where upwards gliding of the dislocation occurred. And along the direction of the slip plane and across the indent, sink-in was observed on the edge of the indent. And as you can see in the AFM profile in figure F, both pile-up and sink-in will occur on the prismatic plane. So this could be due to the slip magnitude for the materials exhibit high hardness, but with soft slip systems, the tensile stress develops when the slip is restricted, corresponding or leading to the sink-in region. In addition to the AFM scan, we also have done the ECCI electron channeling contrast imaging on the both surface and cross section of the both prismatic and basal plane before and after indentation test. And you can see from you can see this dislocation slip planes are quite consistent with the AFM's observations of 2 and 6 fold. The cross section on the prismatic orientation shows the impact of the different slip planes, which forms an angle of about 120 degrees. And for the basal plane, you can see the dislocation mainly glide downwards along the 1010 plane system. So these are the quasi-static load. And in addition to this, led by my previous colleague, Francois, we also investigated the temperature and the strain rate effect on mechanical response of single crystal tungsten carbide. And here I put both quasi-static and the nano impact test results together, despite the two have different setups. So on the image on the plot on the left, it shows the heating stage of both the heating stage for heat up both the sample and the indenter. And the standard load displacement curve were collected for the hardness and the modulus analysis, and the depth profile with temperature and the nano impact test is shown in the figure on the left, and which was further converted to instantaneous strain rate shown in the figure on the right. So you can we can achieve a large range of strain rate from 10⁻³ up to 10 power of 3 or even higher. So the impact test is carried out at up to 600 degrees C here, and we will compare the results with quasi-static at the similar temperature for both grains. Here to mention for the nano impact test, we used the spherical indenter and with radius of 5 micron and pendulum acceleration distance of 25 micron and acceleration force of 5 millinewton. And with the displacement with recorded displacement data as with time, we were able to calculate the velocity, and which was used to calculate the dynamic hardness according to the energy method here, and without including the work of the acceleration force. Due to the depth recorded during the first bounce is not purely a plastic response. The volume of the indent was mirrored with built-in 3D scanning with a sharp indent at very low load of about 1 micronewton. And the crater of the indent is shown as indicated in the yellow images on the right. So as knowing the velocity, the inward velocity, which is when the impact occurred, and the out velocity, which is the first rebound velocity, we also calculated the dissipated energy, which is a good indication of the degree of the plastic deformation and the impact test. And it's for both basal and prismatic systems, the dissipated impact energy are given in the figure in the left. As you can see, for the prismatic orientation, the dissipated the plastic or dissipated energy kept a constant level of about 70%, while the basal plane is increased from about 36% to 60% with increase in temperature. So this is kind of consistent with our observation for the quasi-static test up to high temperature, indication of the plastic deformation along the certain planes, and which the dislocation with more dislocation system triggered with increasing temperature. So here we plotted the hardness and the dynamic hardness of the two tungsten carbide grains, and to summarize the image, we can see there are strain rate dependent behavior regardless of the orientation of the grains, revealing higher hardness at high strain rate at temperature up to 200 for both, and across the entire range of tested temperature for the prismatic and basal orientation. The difference between hardness and quasi-static hardness and dynamic hardness is not very clear, but it could be from changing of the deformation mechanism, and also we observed for the impact test for the impact test on the prismatic grains. When temperature above 200, the large plastic deformations was observed, and the results here we also checked the cross section of the two grains after impact test, and also on the from both quasi-static and impact test modes. We checked the both surface and cross section ECCI images, and we could see they show similar dislocation patterns and the slip planes, which shows with the deformation with the high temperature is carried until is carried out at higher strain rate. So that's the summary for the tungsten carbide test, and here, so next part is for the single and multiple impact test on the coatings, and we have done the test on both DLC and titanium nitride coatings on onto steel substrate. So similar as the tungsten carbide, we have the depth data as a function of time, and in the figure A is the depth profile at different acceleration load, and we then further calculated the velocity of the and the different acceleration loads. As you can see, the maximum velocity increases with the load, and then further calculated the instantaneous strain rate for the acceleration loads, and the similar as the display with velocity, the strain rate increase with the increasing of the acceleration load. by doing the multiple impact test, we found that we could map the coatings property as with the load and also the cycles, the impact cycles. So the left side is the ICM images of impacts at loads of 50 millinewton with cycles from 1 to 50. And you can see the coating start to peel, or the coating start to fail when the about 5 cycles. And on the right side is the lower acceleration load of 20 millinewton, and you can see the failure of the coating started at quite a later stage, and there are a plateau of with the load and cycles, which you can see from this multiple load depth profile with impact cycles. So here you can see a large jump of the impact depth, which corresponds to the failure of the coating. And before that, for instance, for the acceleration load of 50 at the initial cycles of less than 10 cycles, you can see the radial cracks and also circular cracks. But this doesn't lead to the sudden jump of the displacement. Why for the 20 millinewton, the depth stayed constant until quite a higher load. Here we see 70 cycles. So from this observation we conclude that it's possible to map to map the coating's durability as a function of the loading cycles and the acceleration falls. And this work was led by my colleague Abdul on the nano impact test on titanium nitride coatings. We have for this test we have carried out a range of tests from loads of 5 millinewton up to 55, and also single to 7,000 500 cycles. So by mapping this, the depths in the impact depth data from multiple multi-cycle micro impact testing on titanium coating, you can see a complex map on the right to indicate the coating behavior. And the dot here, it shows the failure of the coating corresponding to the 55 millinewton in this case, for instance, for the 55 millinewton 600 cycles images here. For that, we have come to the summary for the nanomechanical test on coatings. Here, I want to emphasize that for nano impact test, it has a great potential to be used as a standard tools in coatings screening and optimization, where the coating durability is tested under interrupted contact situations, such as metal cutting and erosion. And I'd like to thank my colleagues, current and previous colleagues from NPL and collaborators. Thank you.
Thank you very much, Hannah. It's a very interesting presentation and lots to take in. I'd just like to remind everyone watching to please type some questions into the chat. We'll deal with those very soon. But for now, we will have a presentation from Professor Van from Micromaterials. Let me invite Ben to the stage. Hannah, am I leaving stage for now? And we'll have you back for the Q&A. Thanks. Okay. Hello, Ben.
Hi, Sam. Can you hear me okay?
Yes, loud and clear. There you go. There's your slides.
Okay, thanks so much. So after that high-level talk from Hannah, this is just a little run-through that one of my colleagues has prepared about a nanotest extreme system, which you've heard quite a lot about from Hannah and a lot of the different things the multifunctional system can do. This is mostly around its capability for high-temperature indentation testing. So we can achieve high levels of vacuum, so 10 to the minus 6 millibar as standard. We can certainly achieve better than that. The system can be configured with two different loading heads, so a low load head for 0.5 newton and also a high load head up to 30 newtons. Max operating temperature 1,000 degrees or so. And we can also use it as a multifunctional instrument, so we can do indentation tests, nano and microscale scratch and wear measurements, and also these impact tests that you heard Hannah describe as well. And all of these things can be done in conjunction with our nano-positioning staging, allowing us to image and precisely target the features. And a lot of what Hannah was talking about was being able to target specific grains in the tungsten carbide, and that's all achieved because it's possible in the nano-positioner in the system. So why are we using vacuum in the first place? Well, it's to eliminate oxidation on the tip and the sample side. So diamond itself will graphitize in air above about 400, 450. It's relatively slow if you're not heating the tip, as you don't necessarily need to heat the tip for impact experiments, then as you can see with Hannah's talk there, you can go to a little bit high temperatures and still use diamond. But otherwise, we do use different indenting materials for testing other materials in indentation testing. So the vacuum allows us to go to higher temperatures compared to the environmental control in ambient or gas purge chambers that we also offer instruments like our Mantis Advantage. So this is a slide from Oxford University, and what you can see on the right there from a nuclear project is that they were trying to test tungsten for this as similar to the application Hannah described in fusion reactors. And there they were looking at the surface of the tungsten after being exposed to an hour in argon at 750 or an hour in forming gas, even at slightly lower temperature. Or and what you can see there essentially is that after an hour in argon, you get a sort of greeny tungsten oxide there all over the surface. It's relatively untestable to understand the effect of ion irradiation and things like that. With forming gas, you're getting still some degradation, relatively localized oxidation, and the vacuum is giving you perfect surface, exactly the same after many hours or even days in vacuum. So there's no degradation. There's exactly the same native oxide thickness as is there at room temperature. And that's down to this very good vacuum level that we can offer in the system. As I mentioned on the indenter side, so indenters do start to oxidize at different temperatures. And what you can see on the right there is a couple of AFM images that was taken at the University of Cambridge. And here you can see one of the top is a Berkovich indenter that has been used for high temperature testing for an awful long time, but at temperatures under 400 degrees, and you can see it's remained pristine essentially, so there's no tip wear. And on at the bottom, you can see that one's literally an hour and a half in argon at 900 degrees, and you can see already there's some pitting and some blunting of that indenter. So that really limits the ability to use these things as reliable high temperature indenters. You need to recalibrate quickly. So to fix this, you can use these high vacuum conditions that you can achieve in the nanotest extreme system. The other things that you do need to consider is particular chemical reactivity between the indenter tip and the sample, which may happen at high temperature, even if it doesn't happen at low temperature. So on the left there, you can see degradation of the diamond indenter after in contact with a ferrous alloy, a steel sample, and with carbide formers, diamond indenters should not be used at high temperatures. Similarly, on the right, you can see diamond Berkovich indenter in high vacuum. Nevertheless, it's been indenting nickel, and in this case, there's a flat end on the side. So that's not the indenter of choice that should be used for nickel. We use typically sapphire for testing nickel-based superalloys at high temperatures, and those are fine. So there's a little bit more about this. I recommend this review paper. It's quite a few years old now. It's not absolutely perfect, but it gives a very good guideline into the type of reactivity that you might encounter in the materials choice that you might want to use. And we typically offer different indenter materials, so be it sapphires, be it cubic boron nitrides, tungsten carbides, or diamond, to allow you to test the widest range of different materials at these high temperatures. So I think Hannah said, we've been doing high temperature nanomechanics at Micromaterials for a long time now. And relatively recently, this high temperature publications note has been put together and updated just this year. So this has a list of 76 of these different publications and covering a wide range of different materials types. And that can show particularly how you can do reliable measurements and using understanding the tip sample chemistry as well and the environmental control. So it's a popular system now, the nanotest extreme, for high temperature vacuum nanomechanics, particularly going very high temperatures, but also, as Hannah showed, also interestingly now this extension to very low temperatures as well to extend the range of the instrument. A lot of this is achieved through having this very high vacuum level to eliminate the oxidation and cold stuff for the icing. And we didn't really talk about it, but actually one of the key things that is the advantage of this system is this isothermal control by active tip heating of the indenter and the sample. It really gives these ultra low thermal drifts that give you reliable results at very high temperatures, particularly where you get a lot of creep happening in indentation creep happening in many materials. So you really do need to get a good handle on the thermal drift and minimize that thermal drift so your results are reliable. Applications there for particularly things like superalloys, high entropy alloy ceramics, and other advanced materials, hard coatings as well. And there's just a few of our users there on the right as well for the extreme system. Thanks very much. That's it.
Thank you very much, Ben. Okay, so now it's time for the Q&A, which we have a few for us. Let's welcome Hannah back on stage. While she's coming on stage, let me just release the attendance certificate. So it is now available. So please do go ahead and click on that link, but don't leave. We'll still be continuing for a few more minutes. The link will remain active for the next day, so no rush with that. I don't see questions as of yet, so I'll kick off with. I was having to think about what we were talking about different indented geometries. For temperatures, I know we looked at both spherical and Berkovich indenters. Would there be any preference in terms of a specific indenter geometry that you would choose for high temperature testing, or is this something that does not have an effect? Hannah or Ben?
Sorry, can you say again, Sam? Sorry.
So would you ever choose a specific type of indenter geometry for high temperature testing? Once you've selected your appropriate material, would you then think about, okay, do I want to use either a spherical or Berkovich indenter for any specific reason?
I've certainly seen a high spherical indenters used particularly to where elastic modulus measurement is particularly the thing that you'd be after. Creep measurement as well. Sometimes people prefer spherical indenters, but equally pyramidal are good as well. By their very nature, the Berkovich indenters that you use at room temperature typically aren't quite as sharp at high temperature. So if you sort of ever so slightly pre-blunt them, then that geometry stays a lot more consistent at high temperature. So it's exactly the same as if you had a super sharp tip at room temperature. You wouldn't necessarily immediately start using a high temperature.
Okay.
Hannah, that fit with what you say?
I'm just thinking, for instance, we used Berkovich indenter to measure quite small grains. It's just to avoid the cobalt phase effect.
Okay. Actually, just thinking about the grains as well, Hannah. For when you're targeting very specific small grains, are you pre-etching your samples to reveal the grains, or is there another method that you're using to identify them?
For this occasion, we did do the argon iron polishing, which would reveal the contrast between tungsten carbide and the cobalt phase, as cobalt is can be removed easier.
Okay.
I don't think you need a lot of height contrast. I think you just need just a few nanometers or something like that, and then then using the tip as the imaging stylus, you can cut to do an image of a certain area, and then you can use that image to target very accurately. So you just need a little bit of height contrast, and that iron etch I think is sufficient.
Yeah. For most of the work we did before, like with this scanning, 3D scanning, we can locate specific like precipitate or specific structures.
Yeah, I see. I was thinking about, but yeah, if we're using a chemical etch, maybe a bit too severe for something that's going to be so surface sensitive. So yeah, pick a prep method for your grains that's going to be a lot more gentle.
Yeah, Hannah didn't show it, but I think, but actually they're very successful actually at MPL in getting exactly in the middle of the grains as well. So that seems to be very useful. So then, choosing the right grains and getting exactly in the middle, so the stress field remains within the grain and not. So,
I think for most metallic or ceramic materials, which we need to prepare the surface before the test, we can identify the surface features reasonably well.
Okay, got it. So we are coming up to time on an hour. I just want to check in case anyone. There we go, an audience question. Excellent, thanks, Eric. So, Eric has asked a question for Hannah. Was the chromium tungsten nickel transition layer under the DLC coating for improving adhesion to the tool steel substrate? Or what was the purpose of it? How was it applied? This is specific to slide 26, which I can bring up should you need.
I think I'm aware of that slide, and that we do for these coatings we do find there is a buffer layer there, and for specific purpose, for instance, for this case is a commercial coating. I think is we purchased it.
Okay.
I think it's safe to say that certainly one part of that layer is improving its adhesion. There may be some other clever stuff going on in the particular manufacturing. I mean, the sort of chromium tungsten or chromium tungsten carbide is pretty standard for a lot of DLCs.
for adhesion. And yeah, there's other interlayers you can play around with for different effects for DLCs, such as impact energy absorption. But yeah, that would be, if that could be a whole other topic. So it's but yeah. Okay, so we have just one other audience question. So if you both don't mind, we'll take that one and then we can wrap the webinar up. Is that okay? Okay, excellent. I would normally read out the name, but in case I pronounce this horribly wrong, I'm just going to read out the question. My apologies for for not reading your name out. But they've asked how to understand dynamic hardness in comparison to a sort of standard or static hardness. I'd imagine they're trying to ask what's the difference between the two and how to relate the two to each other.
Well, okay. Well, dynamic hardness is often energy per volume, so it's dimensionally the same as an indentation hardness that you get from unloading curve analysis, and it's really the hardness at a given effective strain rate that's much higher compared to that in an indentation test. So by plotting the hardness as a function of strain rate, then you can get some understanding about how the materials become harder as a function of strain rate. So if your application involves contact at high strain rate, then it's more risky, if you like, to rely just on a quasi-static measurement of hardness. So it's a kind of complementary measurement, I think you'd probably say.
Okay, thanks, Ben. Anything you'd like to add, Hannah?
Yeah, I think that's fine. I'm just thinking for the dynamic hardness and the yield stress or dislocation motion on the different strain rates can be complex.
Okay, got it. Thank you. So I think with that, let's draw the webinar to a close. So I just want to say thank you both very much for your fantastic talks today. Very informative indeed. Thank you to Micromaterials for supporting this event. As I always say, we would not be able to do what we do without our sponsors. As a reminder, please do visit surfaceventures.org. You can sign up to our mailing list there, register for new events. Also check us out on LinkedIn. We will soon be updating our website with the information for our next event, which will be on June 27th. I don't have the information to give you right now in order to sign up, but please do check out our website. In terms of LinkedIn as well, please do also visit the Micromaterials LinkedIn page. I've just brought the featured link up there. So please do go ahead and look at that. It's full of lots of good technical information, as Ben sort of discussed earlier in his presentation. So you can find links to the various technical notes and papers there. As well, if you enjoy reading, you can read the fortnightly Modern Surface newsletter, and by signing up to the Surface Ventures mailing list, you will receive this. So with that, I'd like to say thank you all very much for attending. Thank you, Ben and Hannah. And if you could all please tell your colleagues and networks about these webinars, it'd be great for us to continue growing and doing what we do with even more people. So thank you all very much and have a good day.
Thanks so much, Hannah, for a great talk, and thanks very much, Sam, for hosting as always. Very efficient.
Thank you.
And have a nice day, everyone.
You too.
Thanks, everyone. Goodbye.